Alex. I'm a machine learning engineer at Hugging Face and part of the Numina team.
Hello, my name is Jan. I'm a co-founder of Numina.
Hello, my name is Jia. I'm one of the co-founders of Numina.
Hi, my name's Ed. I'm a research scientist at Hugging Face.
Great, let's start. Maggie, how much time do we have for our presentation?
Ideally, 15, 20 minutes, and then that'll leave us time for questions.
Yeah, great. So we do have quite a few slides, so we'll try to be brief and we can provide additional details in the Q&A.
No problem.
So I'll quickly introduce Numina and the project, and then I will let Gia, Lewis, and Ed present our solution to the AIMO competition. So we created Numina at the end of last year. We were actually inspired by XTX Market and the announcement of the AIMO competition. And together with a group of people passionate about AI and mathematics, we started Project Numina with the goal to advance open source AI in the field of mathematics. So here on this slide, you have the key team which participated in the Kaggle competition, but Project Numina had the chance to attract some advisors and some support from companies in the field of LLMs and mathematics. And we had a team of talents who contributed to the dataset, which Gia will present later. So Gia, Lewis, and Ed will now present how we build the solution to the AIMO competition and what helped us win. Lewis, just let me know when you want me to go to the next slide.
Sounds great. So yeah, at a high level, our approach to this problem involved 4 main components. The first thing that we really started with was these DeepSeek math models. Many people in the competition had shown that they get great results just using the publicly available ones. And then we thought, well, maybe we can fine tune our own version of this to do something a bit more targeted for the AIMO problems. And so we fine tuned DeepSeek Math 7B to solve these kind of AIMO problems using pool integrated reasoning. This is where you get the language model to essentially interleave natural language and code, and then you take that code and you execute it in Python, and then you use the outputs and get the model to basically reason about those outputs to make the next step. There's a large amount of literature showing that this boosts mathematical performance, and we also saw that was the case in the competition. So on top of that, we created 2 high-quality training data sets, which altogether come up to about 1 million math problems and solutions. Gia will talk about those a bit later. And that was just for training. For inference, we had to kind of do 2 things. The first thing was to come up with a good decoding algorithm. And what most people do in the field is something called self-consistency, which is essentially you generate many candidate solutions and then you take the majority vote. The main twist on that from our perspective was to add this pool integrated reasoning into this decoding. So in addition to generating many candidate solutions, every candidate solution now has the use of tools, essentially Python, to iteratively find solutions. And the last thing that we found was quite important was with the blind Kaggle leaderboards, in order to sort of make our model selection go fast internally, we created essentially 4 types of validation sets, ranging from problems from AMC, AIME, and also the public math benchmark. Next slide, please. So to give you an idea of what this model looks like when it's doing inference, here we have a demo on the Hugging Face hub if you want to play with it. But basically, you provide a problem, and typically what the model will do is it will provide a rationale, essentially a kind of plan for how it thinks it needs to break down the problem into subproblems. And then it will proceed to generate code to solve that, say, first subproblem. It will execute that code, and then using those outputs, it will reason about it in some way and then decide whether or not it needs to generate more code or just it feels confident it can solve it at this point. So basically, this is how our model works. And if we go to the next slide, can sort of show you how we did it. So there were kind of 2 stages of training. We explored a large range of methods, ranging from reinforcement learning to Kahneman Tversky optimization and other things. It turns out this was the thing that worked the best. And the basic idea was to use 2 stages of fine-tuning. So you've got your base model. It's quite good at next token prediction, but now you want it to get really, really good at these competition math problems. So the first thing we did is we have the data set that Numina has created. This is around 800,000 problems, which Gia will tell us about. And these problems, they have a variety of solutions, which are then templated in the chain of thought format, which really helps the language models kind of learn how to solve these problems more efficiently. So if you fine tune the model on this data set, you get something that we just call the SFT math model. This model is capable of solving math problems relatively well with chain of thought. But we noticed when we submitted this to the Kaggle leaderboard, we were typically capping our performance, I forget from memory, but it was something like around 10 out of 50 or something like this. So we clearly needed to have some additional sort of information in order to get past this bottleneck. So the next step, if Ellen can go, was to integrate this idea of using Python as a sort of tool that the model can use in its reasoning. And so we generated from GPT-4 a data set of interleaved text and code using the code interpreter. And then we fine-tuned the model from stage 1 on this new data set. This is around 100K or 70K problem solutions. And then the resulting model is something that we call Numina Math, TIR, for Tool Integrated Reasoning. And this was the thing that ultimately got 29 out of 50 of the problems correct. So we go to the next slide. Now time for Gia. Yeah, you're on mute.
Sorry for that. So I'm going to talk about how and why we build this data set. In the beginning of the year, multiple studies have shown that it is very effective to fine-tune the LLM to solve mathematical problem using a collection of problem solution pairs. The biggest challenge is when you want to follow the same path, there were very few publicly available dataset, and most of them are at very small scale. So our initial thought of boosting the performance and to also to help the community to progress is to build a very large dataset of problem solution pairs to specifically targeting the fine tuning. We have identified several data sources where we could do massive data collection. The first one being the Chinese K-12 education system, where we could source massively problem solution, a problem with reference solution from publicly available exams. And the difficulty will be less compared to the AIME or AMC 12 even. But in this exercise, you have a lot of arithmetic steps, so that will help the model to reduce the arithmetic hallucination. Some study also show that using synthetic data will help. You could consider it as kind of data augmentation. If you have some very tough problem, by changing some number, you could still make the problem valid, and it teach the model to solve the same type of problem and be more robust. And finally, the most valuable asset of our dataset is the Olympiad dataset we have collected all around the world. The raw data of this dataset are all the PDFs on the different official website of national and regional Olympiad. The biggest challenge was to convert those PDF into text and format them into the right format. Next slide. So if you look at our biggest contribution is compared to publicly available dataset, we have a very large component of competition math problems. So today, the most well-known competition problem dataset that you can use to fine-tune your model is the math training set, which has been built 3 years ago. It contains 7,000 problems. In our dataset, we propose 400,000 challenging competition level math problems. Next slide, please. Here is an example of our process of extracting a problem and pair them with their solution from PDF. So all these PDF are available on the internet. I think this is one of the regional exam or competition in Canada. And so we have two ways to extract problem and solution. Either the PDF is relatively simple, we can do OCR and then use regular expression to match the problem and solution. When it is more difficult, we use manual segmentation to enclose this problem and solution, and then use OCR to convert them to the text format. Next slide. So to give you an overview of all the problem solutions, all the problem statement that we have collected all around the world, we have, especially in the countries where let's say the Olympiad culture is very well developed and you have a lot of students preparing those exams, we managed to collect a massive amount of data. Next slide, please. And once we get the raw data and we convert them to, let's say, the LaTeX or Markdown format, we will process them. The end goal of the processing is to convert them to the what we call the chain of thought format. So to do this processing, what we do is first we convert the raw data. If it is not in English, we translate them into English. And then we ask mainly GPT-4 to, given the reference solution, to rewrite the solution into what we call the chain of thought format. And finally, we ask the model if it is a value output problem to box the output to facilitate the parsing at the end. The advantage of this chain of thought format is it's more detailed, and you have GPT-4 is going to fill the missing gap or the missing reasoning gap or the missing steps. It does not always work, but which provide easy, let's say, more detailed version of the solution, which will facilitate the learning. Next step. Next slide, sorry. So putting all this together, we managed to gather this data set that we are going to open source. And here's a breakdown of the different data source from where we collect all these problems. And then I will add, sorry. And once we get this chain of thought data set, as Louis mentioned, we realized in the beginning of the competition the importance of using code reasoning. Well, this is thanks to one of the public available solution, which pointed out that the importance of using code. So we, let's say we at the beginning of the competition, we tried to derive a two integrated reasoning dataset from our previous Numina chain of thought dataset. We select around 100,000 problems with value output. So they all have, most of them are integer. And then we iteratively ask GPT-4 to produce a two integrated reasoning solution. We apply what we call negative sample rejection. So to reject those samples, those solutions which does not match the correct answer. So it's not just asking GPT-4 to solve the problem, but also we filter the solution which are wrong. And finally, we do a second stage fine-tuning to as Louis mentioned, to get our final model. Next slide. I will let Ed explain our inference method.
Sure. I'm just going to talk briefly about our model submission and evaluation. So this is actually what we ran on Kaggle. And there were a number of things we had to address. One was to do with variance. And so there were 50 problems that were presented to us on Kaggle, and these were presented each time in a random order, which we didn't know. And so methods like early stopping based on the time left would produce quite a bit of variance because hard problems might be coming first or last, and that changed the result. And I linked actually to there's a thread here on the Kaggle forums that sort of showed that you could get variance of say 15 to 23 problems solved out of 50 just because of the ordering of the problems. And the second thing we had to address was that the Kaggle pipeline was running on 2 T4 GPUs, and they don't have a lot of the modern hardware implementations that many LLMs need for fast inference. For example, they don't support flash attention 2, and they don't support bfloat 16. And so we had to kind of work around these constraints in order to get our solution to work. Next slide, please. And so to tame the variance, we didn't use early stopping at all. We focused on a VLM solution for fast inference and model quantization, which I'll address on the next slide. Our approach is as follows. So we have a problem on the left here. We feed this to our LLM, which is going to take the problem, output a description, and then Python code, which we will execute. In this case, we generated for our pipeline 48 candidate solutions. We then execute this code, and there are sort of three possibilities here. One is the code runs, it outputs a value, and we consider this to be a candidate solution to the problem. The second is the code, say, times out or raises an exception, and we feed that exception back to the LLM, and the LLM performs error correction on that code to generate new code. And we perform up to 3 iterations of this kind of self-feedback. And then the third sort of situation is the model outputs an answer that's incorrect. And these candidates, so there's 48 candidate solutions provided for one problem, and then we perform majority voting over these candidates. We also have some other pruning techniques based on whether the output of the model is actually kind of valid text. If the model just outputs like no code, for example, at all, we wouldn't consider that solution to be valid because it's probably hallucinated an answer rather than actually use a tool integrated reasoning. Next slide, please. And so the other thing we had to address were the constraints of 2 T4 GPUs. And so one of those constraints is VRAM. You only have 32 gig of VRAM. And so a 7B model, if you load it in 32-bit, is like 28 gigabytes of VRAM, which is obviously quite a lot, so you don't have much space for activations, etc. And so one thing we did do is to reduce the size of the model using quantization to 8-bit quantization. We used AutoGPTQ. It's a library for activation-aware quantization to perform this. And we also used VLLM, which supports these quantization methods out of the box for faster inference. And we found that like VLLM is much faster than, say, native transformers for inference. Yeah, next slide. And then in terms of model evaluation, to speed up our evaluation, we ran internal evals on the quantized models on our cluster, and we focused on like 4 data sets we created that were these AMC, AIM, and subsets of the math benchmark for evaluation. And we found that AMC and math level 4 and level 5 were quite well correlated with the scores they were getting on Kaggle. And yeah, through these approaches, we managed to have quite a robust solution. And I think this is one of the reasons why on the public leaderboard, we were getting 29. And then when our model was evaluated on the private leaderboard, we also got 29, whereas we saw a lot of other solutions vary a lot in their performance between public and private. Next slide. And yes, so we also compared our models on the math benchmarks. This is a very popular benchmark for math. So we have this 2-stage training, and so we get like 56.3 from the chain of thought, and then tool integrated reasoning from 68.2 for tool integrated reasoning, and this is outperforms like models of the same scale. Next slide. I think it's you, Gia.
Yes, well, we still have 2 minutes, so let's go through some interesting findings, mainly some interesting example of our model output. So we do notice one of the limitation of the evaluating this LLM with value output or value-oriented evaluation. It also explains why co-integrated reasoning works so well. Like in this exercise, if you read a bit the code on the right-hand side, so the exercise required the model to find all the non-negative integer solution for a certain equation, and the model here will just do a for loop to search among the first integers to see if there is a solution. And being very lucky, the model is able to find the only solution to this equation, and without justifying why the ideal way maybe to do it is to explain why you could stop at 100 for X and Y. So this is one interesting example, meaning that sometimes the model get lucky because it's just searching for the most obvious solution, and most of the time for this difficult problem, the obvious solution could be the only solution of the problem. Next slide. And the finding too is for more difficult problems, even though the train of thought model, the two integration reasoning model is able to produce the right result, but from a human reasoning perspective, we might prefer the train of thought model. So if you look at this exercise, for those who have done a bit math or competition level math, you could very quickly spot that the group of equation could be decomposed into a linear equation, which can be solved very easily, and then you could compute the value required, demanded value very fast. So it's not a very, it's a bit complicated problem, but it's not extremely challenging. So if we look at, next slide, please. So what's funny is if we look at the two integrated reasoning solution, it's not doing this at all. It's going to reformulate a bit the equation. And next slide, please. And it's basically relying on the numerical solver of SymPy to find the numeric solution of XYZ. But what's funny is that if you get the numerical solution, you lost the algebraic expression. But the model get lucky enough when it tries to compute the final value. Next slide, please. It gets something without rounded error, so it's exactly a fraction, at least something that could be converted back into the fraction, and it managed to get the final result. Next slide, please. If we require the model to do chain of thought, meaning that do the reasoning without code, sorry, the letter or the words are a bit small, but if you look at the left-hand side, the model start by doing something which does not make any sense. It's telling you 2 to the 13 on 12, it's equal to 1. But never mind, and then it realized that, okay, we could simplify the problem into a group of linear equation, and it started solving it, but it basically forget how to solve a linear equation. So it made a small mistake toward the end, but basically it's getting the tricks and it's very close to solving it completely. So to summarize, the two integrated reasoning, meaning using code, is critical to have great performance on this benchmark, especially for small model where you might have you will be able to reduce a lot the hallucination phenomenon. And secondly, we have proved that our dataset allows to train a very good model to win this competition. And this will be completely open source and will empower the community for the future Progress Prize or even the Grand Prize. And thank you for your attention.